Today we're going to be talking about the shapes of molecules and why they have their particular shapes and what is causing those very predictable shapes to appear. So if I'm thinking about molecular shapes, fundamentally at core, identically charged particles repel each other. So all electrons are negatively charged, so they will all push each other away. That's the basis of what we call VSEPR or VSEPR theory. See, negative charges repel. So what does VSEPR stand for? Well, it stands for valence shell electron, because that makes sense. That's the electrons that actually participate in chemical bonding, the valence shell. Pair, because we either end up with bonding pairs shared in a covalent bond or lone pairs on one atom. So valence shell electron pair, and repulsion, because all electrons are negative, they will all repel each other. The idea here is that since they are pushing away from each other, we want to get them as far apart as possible so that they have less energy to push on each other. So in talking about that, we're talking about two different things. One is electron geometry and one is molecular geometry. Electron geometry counts the areas of electrons around the center atom. So what counts as an area of electrons? Well, bonds count as an area of electrons, and lone pairs count as an area of electrons. And one key thing to note is that all bonds, whether they're single bonds, double bonds, triple bonds, they all count as one area of electrons. When we think about what's happening in bonding, whether we have an overlap between two atoms, then it kind of makes sense that they all count as one area, because even if there's a double bond, it's two pairs of electrons that are overlapping and shared between the same two atoms. So the molecular geometry, on the other hand, fundamentally is based on the electron geometry. We have to know that first. And so that's part of the reason it's so important to start with a Lewis dot structure, because the Lewis dot structure tells me how many bonds and lone pairs I have. But the molecular geometry is different because it's just going to consider the shape of the molecule, the actual atoms that are bonded together. So a little hint is that when you have lone pairs on your center atom, that's when you know that your molecular geometry will be different from your electron geometry. If there's no lone pairs on the center atom, the molecular and electron geometry should be exactly the same. To talk about areas of electrons, let's look at a couple of examples. So here's a molecule that's great for looking at what we are really counting as areas of electrons. Nitrogen triiodide. And sometimes students get really confused because they think there's just so many electron areas here. And then we have to remind folks that when we're doing this, we only consider the center atom when we're talking about VSEPR theory. So the only place I'm counting areas of electrons is what's around that nitrogen atom. What's around the iodine atoms is not what I'm looking at, just the nitrogens. So if I look at that and I count, well, a bond counts, that bond counts, that bond counts, the lone pairs count. So that actually has 4 areas of electrons. So one thing to remember is that lone pairs on outside atoms do not count towards the number of areas of electrons. You're only considering what's on the center atom. Another thing that might help us remember is looking at the example of formaldehyde, this carbon, oxygen, hydrogen compound. Remember we said we count all bonds as 1 electron area each. Single bonds don't count any less than double bonds. So if I look at this one, that counts as 1 area of electrons around the carbon. That's one area of electrons around the carbon, because double bonds only count once, triple bonds only count once. And that's a bond. All of those bonds are equally one area of electrons. So this molecule has 3 areas of electrons. Double bonds or triple bonds don't count extra in VSEPR theory. They only count as one area of electrons because they're still overlapping between the same 2 atoms. So if we're thinking about angles, let's remember a few angles. If I go all the way around, that of course is a circle, 360 degrees. Halfway around would be a half circle angle, or 180 degrees. And if I split a circle into 3 equal parts, I get 120 degree angles. And so these are some numbers you might want to keep in mind while we talk about our next sets of molecules. So we're going to start by looking at the simplest case, 2 bonds, which means we have 2 electron clusters or 2 electron pairs or 2 electron areas. An example here would be beryllium dihydride. Those bonding pairs on the beryllium are going to try to repel each other and get as far apart as they possibly can. The farthest they can get is 180 degrees away from each other. And that means that this molecule looks like a line. And if it looks like a line, we might as well call it a line. So this is a linear molecule. Its electron geometry is linear. And since all of them are bonds, the molecular geometry is linear. So I can kind of get this into a 3D shape for you so you can see that. And you can see how it is all flat, all in one plane, looks like a line. You can also put it in what's called a space filling model. And you can see the same relationship. But not just molecules like beryllium hydride are linear. If we remember, even though carbon dioxide actually has a total of 4 bonds around the carbon, double bonds only count as one area of electrons. So carbon dioxide only has 2 areas of electrons around its center carbon. And so just like beryllium dihydride, those get as far away from each other as they can, and carbon dioxide has a 180 degree bond angle and is in fact linear. Its electron geometry and its molecular geometry are both linear. So looking at it, you can see even with that double bond, because those electrons are overlapping in the same area, it still ends up being a linear molecule. There's my space filling model. You can see the same idea. So there's 2. 2 is linear. When I get up to 3 bonds, that's 3 electron clusters or areas of electrons. One example would be boron trihydride, which has that incomplete octet. Then I divide my circle into 3 separate parts and I get a 120 degree bond angle. That means I need a name that's going to tell me these 2 pieces of information, that this is flat and that there are 3 of them. Well, something is flat when it's in a plane, and so the name for this is trigonal planar. 3 trigonal planar flat. And yes, you do have to have both words. You can't just use trigonal or planar. It has to be trigonal, planar, both words. So if I can show you the ball and stick model that's rotating here, that 120 degree angle gives me a trigonal planar molecule. You can see it's all flat. It's all in one plane. And then my space filling model again, it's all flat. You can see when it rotates up, it looks like a tabletop. It's all flat, all in one plane, trigonal planar. So if you think back to formaldehyde, the molecule that I used a couple of minutes ago to demonstrate counting a double bond as 1 area of electrons. Formaldehyde had a total of 3 areas of electrons too. So formaldehyde would be a trigonal planar molecule with that 120-degree bond angle. When I get into 4 bonds, this is where Lewis structures stop being quite as useful for my shapes. You still really do need to start with a Lewis structure because you need to know how many bonds and how many lone pairs you have, and that's the job of a Lewis dot structure. But this Lewis dot structure looks like it should have a 90-degree angle. And we are 3D things living in a 3D universe, so in a 3-dimensional shape, I can actually get these electrons farther apart from each other. So once we get up to 4 and above, we start dealing with a 3-dimensional molecule, a 3-dimensional shape. That shape actually looks like a pyramid shape, a 4-sided shape, which is a tetrahedron. Here's a tetrahedron on screen. And the outside atoms are on these corners of the tetrahedron. The center atom would be in the middle. The fundamental tetrahedral bond angle that you should make sure you know is 109.5. You should definitely know that one, and then know that when we go on to different molecular geometries, we get smaller angles, but 109.5 will work for everything with 4 areas of electrons on the AP exam, so it'll work for me. Here is a tetrahedral molecule, something like methane. Carbon makes 4 bonds. They get as far away from each other as they possibly can to have that 109.5. When you see that rotating, you can really see there's no angle that looks like an L. They're all bigger than 90 degrees. So again, if the molecule is all bonds, all electrons, all 4 areas of electrons, all bonds, the molecular geometry and the electron geometry are exactly the same. So both of those would be tetrahedral. Where things get different is when I start to look at cases where I do have a lone pair on my center atom. Remember my hint, that was where we have a different molecular geometry. This is still 4 areas of electrons, 3 bonds, and 1 lone pair. But now we're looking at just the bonded atoms to look at the shape in the molecular geometry. The electron geometry is absolutely still tetrahedral, 4 areas of electrons. But if I look at the molecular geometry, and I take this into my 3D shape, you can see it kind of looks like this. It has 3 areas of electrons that I can see in my molecule, 3 bonds, but they're not flat. So we call this trigonal pyramidal. And this bond angle is a little less than 109.5. It usually runs around 107 degrees for the bond angles in the trigonal pyramidal shape. And pulling it into that space-filling model, you can really, again, see that shape is like a little tripod. So it's trigonal pyramidal. That's 3 bonds, 1 lone pair. Electron geometry, tetrahedral. Molecular geometry, trigonal pyramidal. I know it's different because there's a lone pair on my center atom. So probably the most famous molecule in the world is my example of 2 bonds, 2 lone pairs. That still adds up to 4 electron clusters. So the shape is still based on that 109.5 3D structure of tetrahedral. The electron geometry is still tetrahedral. And in fact, this bond angle is even a little less. So if the trigonal pyramidal one was 107, this one's actually closer to 105. And so what we call its molecular geometry, when we see it in this shape, you can see it's not a straight line, it's a bent molecule. You can see how it looks like a V shape there. So water is a bent molecule because it is based on that 4-electron cluster electron geometry. You can see it here in its space-filling shape as well. So here's a little chart that kind of sums up what we've been doing, and I kind of suggest maybe making a little chart in your notebook. The steric number can be thought of as the number of electrons, or the number of areas of electrons. So 2 areas of electrons, 3 areas of electrons, 4 areas of electrons. And you can see that no matter what, if it's got 2 areas of electrons, the electron geometry is linear. If it's got 3 areas of electrons, the electron geometry is trigonal planar. If it's 4, the electron geometry is tetrahedral. But the molecular geometry can be different. The molecular geometry, when I have a lone pair on my center atom, will be different. So when I have a lone pair on a trigonal planar molecule, I actually get a shape that is called bent, which is not one you really need to know this year, but you will need to know it for next year in AP. And then when I have 4 areas of electrons, of course, no lone pairs on the center atom, they match tetrahedral and tetrahedral. When I do have lone pairs on that center atom, then I have a situation where they don't match. Move me out of the way here. When I have 1 lone pair and 3 bonds, there's my trigonal pyramidal. 2 lone pairs and 2 bonds, I get that bent shape. And here's my fundamental base angles, 180, 120, 105. It's always good to know that when I do have lone pairs, it does compress the bond angles a little bit. So the trigonal pyramidal is a little less, and the bent one is a little less still. So we'll look at some examples and what this means for the properties of molecules when we start thinking about whether molecules are polar or nonpolar next.